Hello everyone. So we're going to go right back into things. We're going to be looking at data next. So let me just switch over here, and we're going to see uh, what we're how data is being stored in the computer. Well, what we talked about last time when we were looking at hardware is that effectively, if you want to think of it one weird way of looking at it, if you're dealing with electricity as a way of encoding information, what you really want is on or off signals. You want a whole bunch of light switches. Instead of having, it's sort of on, you need data to be either on or off, or the signal to be very nice and clean. So there's electricity in this circuit, or there is no electricity in this circuit. As a result, everything you're using for a computer is based on two, on or off. And therefore your math has to be based on two, on or off. Your logic is Boolean logic, is either true or false. It is not some sort of or maybes in there. It's only true or false. And so what we're going to look at now that we've looked at the architecture briefly is we're going to look at binary. Now, since you might wonder, what is the number 437? I know many of you stay awake at night thinking about this. What does the number 437 mean? Why is it represented this way? It's actually a brilliant numeric system. I think we're going to have one of our later midterm assignments looking at uh, Roman numerals, and you'll realize just how painfully clunky Roman numerals were, like at least compared to the Arabic numeral system, like 437, what we're using here. It went to a whole bunch of different cultures, and pretty much it goes to a culture and everyone goes like, yeah, that's the way to represent our numbers. It is a brilliant system. So what does this number mean? It's the numerals are different than the actual numeric representation. The number it's representing is not those three numerals. The number it's representing is 437 items of some sort. But what this is actually showing is there are 4 100s, 3 10s, and 7 1s. I know you've been doing this since, grade school, so maybe this is sort of, you might say, oh, this is obvious. Except it's not really when you think about it. So what we're doing is grouping these in tens and then 100s and 1000s and then 10,000s. Powers of 10 and how many powers of 10 we have and building up from there. And why 10? Because you look at your hands and that's why, right? The humans on average have 10 fingers, 10 toes, and so powers of 10 seem to make sense. Uh, and if you want to look at it a different way, this is, or algorithmically, you can break it down. We will have 4 10 to the power of 2s, 3 10 to the power of 1s, 7 10 to the power of 0s, 10 to the power of 0 being 1. So for any given number, you could just keep on increasing the power of 10, so multiplying the number by itself, and increasing that, and seeing how many of those numbers there are. You can algorithmically decompose 437 by saying, okay, we're going to start off the number at 10 to the power of 0, so 1, and then next time around through the loop, we're going to make it check out if something is divisible by 10, then check out if it's divisible by 100, then check out if it's divisible by 1,000, and just keep on going that way. It's an interesting and very effective approach to encoding this kind of data. So, Y10, fingers and toes. So, what we're going to be looking at after now we've done some of the architecture is we're going to look at why we briefly looked at programming and architecture and compilation. We'll just quick review of that. And then we're looking at binary, hexadecimal, not just hex, but hexadecimal, and booleans. Uh, and why is this important? Because when you're debugging this, and it does come up, honest to God, I can't make this up. When you're debugging this, you could be you could be spending days looking at this code, not knowing what the heck happened. As soon as you know binary, it just makes sense. So I'll point this out. I'd also like to point out again, these things are everywhere, such as if you ever see 0FFFFFF somewhere, like when I'm doing a RGB value, you'll see for a color in Photoshop, you'll see, well, what color is white? If anyone that's done anything with Photoshop, what color? What's the numeric representation in RGB? Okay, so since you can't respond, it's actually 255, 255, 255 and there's another number in there which is also 255. Black is 0000, four zeros. Two, three, four. Yeah, four zeros. Red will have some combination of have some one really big number and a whole bunch of other small numbers, and presumably the alpha channel, the transparency, which is the fourth number in this set. There's essentially all the colors that you use in Photoshop are broken down into four different numeric components, and this is for artists doing Photoshop. The reason they're doing this, the reason RGB exists, is because computer scientists essentially designed a world that they understood and they could use and they could represent efficiently in a computer. And so the entire artistic world has been forced to conform to what computer scientists gave them, right? The your light switches and your power bars or use zeros and ones. If you use chmod on your if you're using Linux or Unix, there's something called chmod, and you'll be if you do that, you'll be saying, well, I'm going to write 777 for it's executable, writable, and readable for me, for other people, and for the world, for example. It pops up in weird, wonderful ways when you have a flag, and I can't even point out all of the cases, but it's ubiquitous in computer science. If you don't know why we represent numbers in a certain way, you will have no idea why. Like, if you don't know about binary, you don't know why we're doing this. We'll get to RGB values soon enough, but let me just let the cat out of the bag here. It's to efficiently encode what a color is using a byte of information. Actually, 4 bytes of information. That's why we do it that way. So, um, what we have is for our data itself, we've already looked at the architecture. We've already looked briefly at how the various compiled languages work. Computers store numbers in binary because we don't have sort of maybe almost right. We have on or off, and you can think of it as like an array of light switches or switches to toggle things on and off. Uh, and other than I said a few important exceptions, quantum bits, for example, are different. Now these are called bits because they're binary information units of information, binary unit. And so what you end up getting that's just the term that it's used for, and it turns out there's and these are just sort of the fundamental minimal amount of stuff that we have. Uh, but because this data is zeros and ones, it's also extremely difficult for people to use. Theoretically, you could program a computer in binary, just have which bits are on and off, but really it's going to take a really long time to read, really long time to understand. And in fact, the transcription and the errors you would make just reading or writing this stuff would be so egregious that it would just be a fool's errand to do. And I'd cry a lot. I really hate writing assembly. I can only imagine what binary would look like to write for code. So we have a binary digit, which is either 0 or 1, and that is just the minimum amount of information that we could store. Much like a neuron in your head, a brain cell in your head is the minimum storage essentially for your brain. No, our brain don't work like that, but hear me out. This is our minimum unit, a bit. Uh, when we combine, we want to combine these things to represent higher numbers. So what we need is some kind of we want to be able to do math using these binary digits. We also do logic with it, and we want to be able to represent characters of the alphabet. But let's just think about math. If I wanted to do normal math, like I would do with decimal, right? Base 10 math, I can't do it. I don't have 10 fingers or 10 toes on a computer. I have on and off. I need a mathematical system that works with on and off signals. That's it. And so instead of representing 0 to 9, I actually want a number system that represents 0 and 1, and that's it. I can still represent the full set of numbers, but my math that the computer is doing is only doing zeros and ones. I have a little bit of a rant here. My Charles Boole rant. Charles Boole was I think he was technically considered a philosopher, but living in England, presumably well-to-do, given the fact I don't think his any of his publications or any of his work really blew anyone away at the time, is looking at a philosophy or a logic system that is based truly only on true and false. So there's no maybes, there's no like humming and hawing over it. The logic system is based truly purely on true and false. And he sort of flushes out this full system based on just true and false. What's interesting about Charles Boole is I'm sure no one gave two craps about what Charles Boole was doing. Like he's this guy that's just thinking and waxing on about how to do a logic system based on true and false. And pretty much people thought it was a dead end. I mean, you could do only go so far with this, and then you've explored all the things what you can do with a binary with a Boolean logic system named after Charles Boole. Uh, and you can't go much further than that. The world does not work in these black and white terms the way that Charles Boole's philosophy system was supposed to work. And dead end. Who's ever going to use true and false to do stuff? Well, it turns out as soon as you have a machine that only does on and off, it becomes extremely important, as you might imagine. Now, there's no way. The guy's long since dead by this point in time. He had no, there was never exposure, any hint that his work was actually going to be useful to later generations. For anyone that seems to want to say that academic research is useless, I like to point out Charles Boole. Every once in a while, not all academic research is used, but sometimes you don't know when it's going to be used or how it's going to be used. And things like Charles Boole's work suddenly becomes directly applicable to these electronic computational machines that they're inventing, right? Suddenly, Charles Boole's work allows you to do math because effectively you can do arithmetic with just it's a logic system. It's ands and ors to do the calculation. That's why it's an arithmetic and logic unit. It doesn't do arithmetic per se. It's doing a logic system to actually do the arithmetic. We were not going to get into that particular minutia, but under the hood, it's just using Charles Boole's work, which I find fascinating. So, Charles Boole, and quite frankly, if I would love nothing more than in my life to do something important enough that my name is plastered around everything in the entire that would be. I'm not expecting that in this world, but Charles Boole has his name on everything. Boolean logic, Boolean like it's every single time you do anything with an and or an or with a computer, it's Boolean. Um, Binary is a base 2 number system that uses Boolean logic to do the calculations. So our decimal systems are base 10, 0 to 0 to 9. There are 10 numbers in total. There's no 10th, there's no 1 0. It is 0 to 9. Those are the symbols that we have available to us. A binary system is base 2. I got 0, I got 1. And then when I get to 2, what do I write? I got right 1 0. So much like 10 is one group of 10 and 0 groups of 1, a binary number is I get how many groups of 2s, I get groups of 4s, I get groups of 8, I get groups of 16s, 32s, that sort of thing. Every time so if I wanted to calculate my binary numbers, let me just see if I have my pen around here. I don't, I think no, there it is. All right. So I might have some, here is, I'm going to write 2, 3, 4. That's 0, right? I'm going to use 4 bits. I'm just randomly choosing 4 bits at the time. I'm going to use 4 bits to represent the number 0. Here's 1. That's not going to be surprising for anyone. I go 0, 1. Here's 2, though. I can't represent the number 2 anywhere like I can't represent the number 10 in the ones position. I can represent, I go up to 9, and then as soon as I get to 9, I overflow into the next column. So here I'm going to overflow into the next column. It's going to 0, 1, 0. I've overflowed 1 plus this 1 here makes we go over to the 2 columns. So I have 1 group of 2 and 0 groups of 1. I add another 1. When I add 1 to this, I will overflow. This will overflow, and then it's going to cascade over. So 0, 1, 0, 0. So that is the decimal numbers 0, 1, 2, 3, and this is 4 in binary. Okay. When I look at a binary number like 101 in binary, it is one group of 4, zero groups of 2, and then one group of 1. And it forms the exact same pattern as I had with base 10. This is one of those things, if you're not getting it right away, play around with it for a while, it'll come into focus, and then suddenly it'll make perfect sense. Our base 10 number system is not just some random thing that you've memorized. It should not be something you've memorized. It represents something. It is groups of tens, 100s, 1000s, 10,000s. Same thing here with binary. It is groups of 2s and 4s and 8s and 16s, the powers of 2. And which is why most programmers within maybe 1 to 2 years have the first 10 powers of 2 memorized. Not by choosing to memorize it, they're not forcing themselves to memorize it. It just will come naturally because they do it so often. Um, so the binary system is used to store data in the computer. It's either on or off, and it's holding the electrical charge. And since it's less sensitive to electrical variations and noise, it works pretty well for us. There are some weird cases. There's a great Radiolab episode, some questioning on it, but there's a great Radiolab episode called BitFlip. If you want to have listen for it, it's fantastic. At least I like it. It slowly goes over how binary actually works. So random things like, honest to God, a cosmic ray can actually accidentally flip one of these bits. It's just an electrical signal. And if you don't have redundancy in your data, if you do not have that data stored in multiple places, these random occurrences where the bit accidentally flips over can radically change the data you're storing. And then you record or save that data somewhere else, and then you've encoded the wrong information. Now, in case you're wondering what um, why doesn't our brain have this? Our brain actually misencodes things all the time. It's a different system, completely different system, but we misencode memories and all sorts of things on a regular basis. This is just the computer version of it, that the bits that you're storing can accidentally go off, but due to random events. Um, so we have binary. It's base 2. It will, so if I want to store 0 to 15, I need 4 bits. It will store up to, but not including, the number 16. That is 2 to the power of 4, 16. So if you have 8 bits, we get 256 combinations. That's 2 to the power of 8. Yes, I have that in my head. Or I can also read the slides, I suppose. Uh, so here is 256 in binary would look like this. 255 in binary looks like this. It's all ones. Why is it all ones? Because it is the largest number I can represent with 8 bits. This is 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3, 2 to the power of 4, 2 to the power of 6, and 7. If I add up all of those bits, I will get 255. I happen to know this just off the top of my head. So here is, and that is effectively the reason why RGB values or color values are the values 0 to 255. They are a byte of information. We'll talk about bytes in very, very shortly, but it is a byte of information, each of those colors. There are 3 component colors, red, green, and blue, RGB, and then there's a transparency value, another number that it gets stored around. And with those 4 numbers, I can represent most colors that are humanly visible. Not all, but close enough for computer work, at least for a while. And so encoding color using this system allows me to easily represent things and not have, it allows me to break down a big nasty problem into these little component parts. Alright, so binary will have a most significant bit, will have a least significant bit. Depends on what system you're using, where the most significant bit and least significant bit is in space. Quite frankly, it doesn't really matter for our scenarios. What do we actually put the most significant bit on the left hand side? What's the left hand side on a computer, right? The orientation of the computer should not make any particular difference. How it's stored in the registers shouldn't, it will make a difference, but left and right doesn't really make sense when you're talking about a computer. So there are systems called Little Endian, and Big Endian is named after. I thought it was some horrible, horrible term. It turns out it's a term used for the orientation of the eggs which people were eating in the book Gulliver's Travels. Weird, weird. Anyways, weird thing, weird reference for where Little Endian and Big Endian come from. Uh, but the idea is, for a long while, Windows machines and Macs read data in the opposite direction of one another, and it led to all sorts of fun wackiness. For our case, we're going to say the most significant bit, let's say, is on the left-hand side right here. This is the bit that records whether I have a 512 or not. The least significant bit is the smallest number. Much like 432, the most significant digit is the 4, and the least significant digit is the 2 in 432. So let's put a 2. Let's just erase that 2 because that looks terrible. Let's put it as 2. Okay. Most significant digit, least significant digit. I guess that's why they don't really write that as an acronym. LSD is a very different thing for most people, especially for the Beatles. Okay, so 432, this is the most significant digit, least significant digit. We're doing the same thing with binary. Most significant bit is the bit that counts, has the most weight to it. Least significant bit is the bit that carries the least amount of weight. It's a 0 or a 1. And so let's do some math here. So let's take some binary number like 0 or 1 0 1 0 1 0 1 0 1 0, this entire thing, this nasty thing. How do we figure out what the value is? We could essentially go bit by bit, either from the least significant or from the most significant, doesn't really matter, and say, okay, we have this one right here. Well, actually, we have it down here. So let's look at this. So for the ones digit, I have a 0. So that's not adding to my total. For the twos digit, I got a 1 right here. So so that's going to be added to my total. For the fours digit, or the 2 to the power of 2 digit, I have a 0, so it's not going to add to my total. There's a 1. So for the eights, for the 16s, I have a 0. For the 32s, I have a 1. For the 64s, I have a 0. For the 128s, I have a 1. For the 256 position right here, I have a 0. And then I have a 512 for the 1. What this means is it's 512 plus 128 plus 32 plus 8 plus 2, and you add them all together, and that's the binary representation of 682. Very much like this is 6 times 100 plus 8 times 10 plus 2 times 1, right? This is 1 times 512 plus, or 2 to the power of 9, plus 1 times 2 to the power of 7, plus 1 times 2 to the power of 2 to the power of 5, plus 1 times 2 to the power of 3, plus 1 times 2 to the power of 1. That's, or yeah, 2 to the power of 1. And that's how you would actually interpret this thing. Notice as a little weird side effect, you'll know if something is odd or even. If this bit here is on, it is odd, as in it has a 1 at the end. Otherwise, it is even if it has a 0. 682, 683 would be, I would have a 1 at the end. All right. This is one of those things that you want to practice a little bit just to make sure you have it down cold. The question is, how do I come up with, so if I have a binary number, I can convert it to decimal, and for me at least, I will actually write out those powers of 2 and make this little table at the bottom. Just like this. I will put a 512, 256, 128, 64, or just 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, that sort of thing. I'll put down my ones in the position. So if I start off with this number here, I'll put down the ones in the particular place, and then I will do this addition just like I did there. So if I have a number, let's do a 4-digit version of it, 1011. So this is this one right here is, I'll just do it a bit slowly, 2 to the power of 0, 2 to the power of 1, 2 to the power of 3, 2 to the power of 4. All right, that can't be right, 2 to 2. I was able to find my mistake, notice, because I cannot have 2 to the power of 4 with a 4-digit number. It goes 0 to 3. And that's where I just made a little screw up in there. Okay, 0, 1, 2, 3. That looks more like it. What's 2 to the power of 3? Which is equal to, 2 to the power of 3 is equal to 8. 2 to the power of 1 is equal to 2. Plus 2 plus 1. Notice I have a 1 at the end. It means it's going to be an odd number. I can double check my work that way. So it's going to be an odd number. So 2 plus 8 plus 2 is 10, 11. So this is actually 11 in binary. Okay. If I want to go the other way around, if I want to take a big number like 682 and convert it back to, and convert it to decimal, convert it to binary, how do I do that? Well, I got a bunch of different approaches. So here's the most significant bit approach. Most significant bit approach is this. I will take the largest binary, like power of 2 that I can come up with. So I find the power of 2 that is the largest that is smaller than the number I'm looking for. So for 682, the next closest but smaller power of 2 is 512. So I know that the 512 bit must be on. This bit right here must be on. Okay, so 682 minus 512, that's whatever is left in the rest of this number here. Whatever is left of the rest of this number here is going to be what's remaining. So 682 minus 512, that leaves me 170 left over. Okay, 170 left over. What's the next power of 2? Well, it's not 256, not 512. It's 128. That's the next closest power of 2 to 170. So I'm going to subtract that. 170 minus 128 gives me 42 left over. That's whatever's left over for the rest of this thing. This chunk right here, what is remaining, is going to be equal to 42. Okay, so I'm going to plop a 1 down here. I'm going to take 42. What's the next power of 2? It's not 64. It's going to be 32. 42 minus 32, that means whatever after the 32 is going to be equal to 10 in total. And I put down the 1 in the 32 position. I take my 10. What's the next power of 2? It's not 16. Oh, 8 is the next closest power of 2. 10 minus 8 is giving me 2. So whatever is here is going to be left over is going to be equal to the value of 2. 2 minus 2, so I can get rid of this thing, gives me 0. As soon as I get to 0, I'm done. So in case you're wondering, in case you're confused, or in case you're concerned about doing it right, I love the fact that this system works. You can work both ways. So if I tell you to go from a binary number to a decimal number, you could go from binary to decimal and then decimal to binary again to double check your work. If you get back, if you reverse engineer it and get the same number again, it means most likely your math is right, unless your math is consistently wrong. So that's the most significant bit version of it. I keep on taking the power of 2 that's closest to the number I'm looking for, keep subtracting off powers of 2 until I get to 0. So we can try other examples of this. This is just, one of those things you need to practice until you make it your own. I keep on taking the next power of 2 that is close to it, subtracting that off, seeing what's remaining, keep on doing that. All right, here is the alternate approach. I'm going to go with the least significant bit approach. I'm going to keep on dividing the number by 2 again and again and again and again, and seeing if I have a remainder. Again, if I'm saying, let's say 11 mod 2, what is that equal to? In case you're forgetting what modular arithmetic is, it is what is the remainder. If I divide 11 by 2, I don't get 5 point something, I get 5 with a remainder of 1. In terms of whole number arithmetic, it's something like this. For whole number arithmetic, I don't get, so if I divide 11 by 2, I get 5 with a remainder of 1. I'm not dealing with 5.5, 5.333, or anything like that. I will get a whole number and I'll get some remainder. That's when we're talking about a discrete math approach to doing mathematics. If we're talking about whole numbers only or integers only, I don't get fractions, I don't get decimal points, I get whole numbers. It comes up very frequently, especially when we talk about integers. So what I'm going to do is I'm going to keep on dividing the number using whole number arithmetic. I'm going to keep on dividing by 2. And every time I divide it by 2, I also want to find out if I get a remainder. So 682 divided by 2, do I get a remainder? No, there is no remainder. It's an even number. So that'll give me 341 with remainder 0. 341 divided by 2 does give me a remainder. It's an odd number. So that's 170 with remainder 1. Right? 170 plus 170 plus 1 is equal to 341. 170 divided by 2, well, 170 is an even number. Divided by 2 is, I'm going to get 85. 85 plus 85 is 170 with remainder 0. 85 divided by 2, that's an odd number, so I'm going to get a remainder. 42 plus 42 is equal plus 1. 42 times 2, or 42 plus 42 plus 1 is equal to 85, right? So I keep on dividing this number by 2, and then I figure out if there's a remainder left over. 42 is an even number, so if I divide it by 2, I shouldn't get a remainder. I'll get 21, right? 42 divided by 2 is 21 with remainder 0. 21 with no 21's an odd number. It's going to give a remainder. 21 minus divided by 2 gives me 10 with a remainder of 1. 10 plus 1 gives me 21. Do it again. 10 divided by 2 gives me 5 with a remainder of 0. 5 gives me 2 with remainder 1, right? It's not evenly divisible. 2 divided by 2 gives me 1 with remainder 0, and then I have 1 divided by 2 is equal to 0 with remainder 1. So I should actually put that other one in there. Just to exhaustively do the very last bit. Okay, but here's the kicker for this whole thing. That's reverse order. What I want to be able to do is I'm going to put down that first one, the most significant bit, 1. Then the next number right here, this 0, is the next significant bit. I'm going to go this way up this line. 0, 1, 0, 1. Okay, so I got 0, 1, 0, 1, 0, 1. So far, so good. 0, 1, 0, 1, 0. Let's check our number here again. 1, 2, 4, 8. That should be, that's 10 numbers in here. Let's see if we had 10 numbers here. Yeah, we had 10 numbers here. Right? I regenerated the exact same number I had last time. The difference is, the big difference between these two approaches is this, I need to, as a human, find the next power of 2. And when those powers of 2 are ridiculously big, like, I don't know, 2 to the power of 397, hard to do. I can't do that in my head. This, I just got to keep on dividing by 2 over and over and over and over again until I get my number I'm looking for. And you can get a computer to actually do this calculation for you, in case you ever wanted to write that as an algorithm. I just keep on dividing a number by 2 each and every time and figure out what the remainder is. So this is sort of the go-to approach for if you're programming this. This is, I find, the more human understandable. I find it a bit more human understandable approach. This just keeps on figuring out what the last bit on it keeps on figuring out what this bit over here is over and over and over again, and then shifting everything over. So I go from this is 682, and then let's go 341. Here's what 341 looks like. 101010101, and let's put a 0 at the front. That's where we are. Right? It is, all I did was shift over by 1 bit. 170 is, I'll put the, I'll, I don't know if I want to put the two zeros, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, right? I keep on shifting over one bit, the whole thing over by one bit. That's what I'm doing by dividing by 2 all the time. All right, so I would like you to try a couple things. I'm going to try 29 next as an 8-bit. I'm going to convert 29 to an 8-bit binary number. And then I would like you to try 47. I'm going to make that a quiz for this week. So you can go online, check the poll everywhere, and take the quiz. This is one of several quizzes when it comes to doing this. Just try it out. Okay? So I would like you to pause the video for a second. We're going to do 29. And then after, you can try it on your own though first. And then afterwards, take the quiz and see how well you do. Okay. I hope you paused the video. I hope you tried 29. So let's try 29 the other way. So 29, what's the next power of 2 that is less than 20? That's actually 16. The next one up is 32. So 16 is the number that we're looking for. So we have 2 to the power of 4 is equal to 16, right? 16, 8, 4, 2, 1. I'm going to keep on separating these things out. And let's put our bits in the right place. So we know we'll have a 1 there. Minus 16. And now I need to figure out what the heck that remainder is. That's 13, right? Stupid basic arithmetic. All right. 13 minus, what's the next power of 2? Ah, it's 8. Okay, so I can put an 8 in here. So I'm going to have a 1 in this position here as well. 8 minus 13 is what? So that's 5. I don't get people in the class to be able to correct my how I say it, my math, unfortunately. So if it's 5, the next power of 2 that we have available is 4. So 5 minus 4. All right. I'm not going to have a I'm going to have a 0 in the 2's position, and then I'm going to have a 1 in this position. 29 is an odd number. The last digit here is a 1. Okay, things are good. Right? We'd expect if it's an odd number, this is going to be a 1 there. If it's an even number, it's going to be a 0. And I've done my numbers. But I need an 8-bit binary number. This is 5 bits, so I'm going to stuff 3 zeros at the end, at the most significant bits. 3, 4, 5. All right. That is 29 as an 8-bit binary number. Let's try the other way. 29 divided by 2. I'm going to have the remainder. I'm going to have a remainder column. So, and then this is where things get a little bit hairy. So that's going to be 14. 14 times 2 is 28. And then there's going to be a remainder 1. 14 divided by 2, that's going to give me a remainder 7. It's an even number though, so I'm going to put a 0. I then say 7 divided by 2, that's going to be equal to 3, right? Remainder 1. 3 divided by 2 is equal to, oh, that should be 1 remainder 1. 1 divided by 2 is equal to 0 remainder 1. So my number, I'm going to write in the right order. I'm going to go from the most significant bit to the least significant bit. So I'm going to make some space here. 1, 2, 3, 0, 1. And then I stuff 3 zeros at the front because it has to be an 8-bit binary number. Whether I use all the bits or not, it doesn't matter. I have a box. You can think of it as a box holding stuff. If the box can hold something gigantic, like it's a giant Tupperware container, and all I do is put a little tiny item in there, who cares? It's still using up the full box, right? The rest of it is, the box is full. It's full of air. Same thing with binary numbers. If it's an 8-bit binary number, it doesn't matter how big the number is. It will the box is that size. It is using 8 bits whether I'm holding a 0 or I'm holding a 5 or I'm holding whatever number. 256 cannot hold 256, so 244. 256 is too big for the box. we'll get what's called an overflow. It's going to lead to a problem. So the box doesn't matter if it's 8 bits. I have to stuff zeros at the front if I'm not using this. There's if I have a 3-digit number for representing 10. So here is the 3-digit version decimal value for let's say 13. It's 013. That's a 3-digit decimal number. Or let's do 4. Make it a bit more obvious. You stuff zeros at the front. You could already do that in math. We just implicitly leave off those zeros. So with a binary number, if I say it's 8 bits, I'm going to make sure I have 8 zeros or ones in a row. Okay. With that being said, we're going to get to I have a couple more things I want to make sure. Decimal binary. Okay, there we go. And okay, we'll get to after we get to there, we'll stop at 2's complement. All right. So most of the time when we use decimal, we is really that we a real number we're dealing with. We don't normally convert to decimal and back again much times. Um, in programming, the type of data that we're dealing with. If I'm dealing with let's say the number 4, you could say it's 4.0. You could say 4. You could say it's 12 over 3. You could say it a whole bunch of different ways because they're mathematical constructs or ideas. When we're talking about programming, the type of data that we're dealing with changes how it's interpreted. It's all zeros and ones under the hood. No matter what we're doing, it's still a 0 or 1. So whether it's a character, a color, or a number, or a floating point number, or whatever the case is, it's still just zeros and ones. It will take up a very specific amount of space no matter what you do. So if I say it's 8 bits, I have zeros in the place. If I'm not using up all the bits, I have zeros in place. I have to use up those bits. They're, they're being used. I have 8 bits. So like a box and only partially filling it, small numbers have a whole bunch of zeros and a bunch of and then ones at the least significant bit position. There's no avoiding that because the math that we're dealing with, it's not a human reading it, it's a computer and they have to blindly calculate things. So no matter what, if I say it is an 8-bit number, you have to show all 8 bits. You cannot show 4 of the bits. It is considered wrong unless you show all 8 bits. The data stored has nothing to do with the space used. If the space used is based on the size of, if I say it's an 8-bit binary number, that's how much space is used, irrespective of the data being stored. And that leads us to something really quirky when we get to 2's complement. That little characteristic is actually why 2's complement works, because there's a maximum amount of data you can store. In 8 bits, I can store 0 to 255. So what if I add 1 to 255? What happens? That's what we'll get to very soon. All right. So just in case you're wondering, a byte, if you've never heard of the term before, most of you probably have, but a byte is 8 bits. People have argued it's not consistently always 8 bits. Originally was actually 6, or for a while was actually 6 bits, because that was actually it was the amount of data you had was very limited. But notice a byte, 8 bits, it's still a power of 2. In fact, it's another it's a power of 2 that's a power of 2. We love powers of 2. I will say that the word byte, the spelling of byte with a y is intentional, because although the English word byte, B-I-T-E, would look the same, and if you accidentally forgot the E, it means something radically different. It means a bit. And so when they were originally designing the byte or talking about the byte, they intentionally spelled it a different way to make sure it didn't lead to that confusion. Hence, byte with a Y. I find that fascinating. I also find it interesting that a bit is 1/8 of a dollar. That actually goes back a long way. They stopped using bits a long time ago. But shave and a haircut, 2 bits. Yeah, a bit, 2 bits is a quarter. That's what the slogan or the jingle is. It's shave and a haircut for a quarter. It's also meaning cheap at the time. So the term byte and it being 8 bits might also be coincidental to that particular thing. I have not been able to find definitive proof other than if you listen to a Sharon Lois and Bram album from the 1970s, which I had my kids listen to it a while ago, they actually talk about bits and bytes, and I'm pretty sure in the 1970s, Sharon Lois and Bram, the kids' entertainers, did not know about computer science. Anyways, neither here nor there. A byte is 8 bits for all intents and purposes nowadays. And it makes our life a lot easier because we just deal with bytes. We don't deal with bits, we deal with bytes. It, just because they're a bigger unit and we can actually deal with more meaningful stuff. It also turns out that the computer does not deal with one bit at a time. The minimum size chunk of data that it deals with ever is a byte. It will take all 8 bits at a time and interpret it. It might take even more than that, but the minimum size it ever deals with is 8 bits. Um, Different operating systems deal with different sizes amounts of data. The amount of data it says as the minimum size unit will change depending on the operating system. So a 64-bit operating system is different than a 32-bit operating system because the number of bits it deals with at any time, the size of a chunk it deals with at a time differs. One would be 32 bits is the minimum size chunk of data it deals with, and the other one is 64 bits of data that it deals with as a chunk. That's what the 64 or 32-bit operating system means. It means how big is essentially a word of data, how big is a chunk of data that it deals with. Uh, and that actually, and the next power up, you'll notice that the bit of your operating system keeps on going up by powers of 2. Megabits or megabytes, and your memory goes up. It doubles, well, it used to double every 18 months. The processing speed doubles every 18 months. Everything is a power of 2. And when we're talking about a megabyte, it is not a power of 10. It's actually a power of 2 that we just pretend is a power of 10. 1024 is a kilo. 1024 bytes is a kilobyte. Is not 1000. Just weird little quirks in history. Um, you'll see powers of 2 everywhere, including there's even a game. So I think that link works. If it doesn't, please let me know. There's a video game 2048 where you're just trying to combine numbers to make various powers of 2, right? Computer scientists love powers of 2. You'll see us use them everywhere. Just get used to how anal retentive we are. We just like things doubling in size, or just, you know, we'll just always deal with the next power of 2. We won't try and increment it by a little bit. We'll just double it as just a general process for everything we do when it comes to programming. If you worry about the problem, you just double it and double the amount of memory you have, or double the amount of RAM, double whatever you need. Okay. As I said, 256. When we talk about eight bits or a byte of information, gives us 256 possibilities. It's the numbers 0, which is 8 zeros, to 255, which an 8-bit variable. Okay, yeah, which is 255 is all 8 ones. And therefore, the numbers you can represent with a byte are 0 to 255, which is, oh, wait, one of our RGB colors, for example. It also pops up in wonderful, weird ways in other cases like chmod. Um, there's no just general rule for how we represent numbers. We have some consistency, but it turns out numbers, the computer is agnostic to it. It has a bunch of zeros and ones. It doesn't know how to interpret it. You tell it how to interpret those numbers. So if I have a byte of data and I say it's a character, it's interpreted differently than if I say this is a byte of data and it's a number. So we're going to be looking at two different things next. We're going to be looking at linear variables, meaning the numbers go up linearly. If I double the number of numbers I'm representing, I need another bit. Uh, so really big numbers need really a lot of bits. Nonlinear variables, like real values, effectively use things like scientific notation. They'll represent decimals, floating point numbers, that sort of thing. And if I increase the size of those numbers, it doesn't necessarily mean I have a much bigger number being stored. We'll talk about those in a little bit. But linear variables have a direct binary correspondence. The number you're representing is represented directly in the binary. There's no real interpretation going along there, or not much interpretation. Nonlinear variables means there's some correspondence. You have some power factor, some exponential exponent factor. You have the number you're representing. You have a sign bit. It The advantage of a nonlinear variable is that you can represent much wider bunch of numbers, including floating point numbers. But my God, they're hard to read and interpret. They're extremely slow to read to actually process when you're talking about the computer processing the number. It's actually a lot harder to deal with, and they're really hard to understand. So the direct correspondence means debugging a linear variable, which we'll talk about next with two's complement. Debugging a linear variable is much easier than debugging a floating point number or a double. And so, to the point that we're not even going to really cover floating point numbers or doubles. They will not be on the exam. They're just too convoluted for people to get their heads around when they're trying to debug and look at the data. Okay. Um, Before we dive into it, I'd like to point out that characters and unsigned characters, integers, unsigned integers, shorts, longs, there's a number of different variable data types in C that are linear variables. If the number gets bigger, the number of bits you need to store that value goes up. Uh, a floating point number or a double do not follow this. They're nonlinear variables. They're the two major types of nonlinear variables. The double stands for double precision, by the way, meaning it has twice the number of bits to store everything. Uh, but they're harder to read and harder to get your head around. Okay, so when we're representing a decimal number, a character value is normally using there is very few consistencies in C, and in fact they can change over time. An integer used to be 16 bits, I do believe. Now I think it can actually be 64 depending on the operating system. In some cases, it's 32. It depends on what version of C you have, what operating system you have, and a bunch of other factors. The size of the chunk, the amount of bits you have to represent an integer number, will change depending on the kind of operating system you're using and the kind of compiler you're using. The one consistent thing we have, for the most part, is a character, alphabetical character, is actually 1 byte, and always should. It's consistently 1 byte. They have not tried to double that size in 30, 40 years. So a character, for the most part, you can sort of bet the farm a little bit on a character being 1 byte, but everything else has variable lengths, and we'll be looking at that later. Um, we're going to be looking at decimal values, how it's being stored for linear variables, and uh, and how it's actually being stored in memory, because you need to be able to debug this later on. So what I'm going to do is I'm going to leave the video now, take a little break, practice some binary yourself, and then come back to the next video looking at two's complement. I'd like to point out, and then after that we're going to look at hexadecimal. I'd like to point out though, the two's complement is used for representing negative values. And I want you to think before we sign off, or after we sign off, think about how you would actually store a negative value with a binary number. Notice we have no negative sign. We have zeros and ones, and that's all we ever have. There's no other symbol sets that we have available to us. We don't have tildes, characters. We don't have nothing else other than zeros and ones to represent everything in the entire universe of possible symbols we have on a computer. The computer only ever sees zeros and ones. So how do you represent a negative number in that case? Okay, when we come back, how you represent a negative number in that case. All right, thanks everyone.